Okay, hello everyone. Thank you for giving me the opportunity. I've been to share with you some data. I've been convinced for years that I needed to have physical oceanographers with me, and it's hard to get them interested because we are very focused on small things often. But I'm very glad here, and I'm a bit stressed to speak about all this process in front of this big assembly. But maybe you will give me good ideas on my data. So I want to share with you data and thoughts about two main field work. So the first one is Mayotte volcano, if I manage to. Okay. So I don't know if all of you have been are familiar with this recent event. It's a major offshore eruption offshore Mayotte. So you see the volcano here, the island, and there is a new volcano that appeared here. You can see the bathymetry data, and it's all new. It's almost 1 kilometer high, 5 kilometer diameter at the base. And thanks to a rapid cruise, it was not so rapid, but as rapid as we were able to go there, we could see a 2 kilometer high plume related to the eruption. So it's really a massive thing that was actually first detected. Thanks. Oh, am I missing? Yeah, maybe I put it afterwards. It was detected by the seismicity first. So a lot of shaking, which was very unusual in this area, but also seen on ground deformation from GNSS. So on the left here, you have the GNSS data. You can see that the island moved towards the east and dropped down by almost 15 to 20 centimeters on the coast. So it's very significant. So we try to react as quickly as possible and put, because when we knew it was offshore, we tried to put seafloor pressure to capture something, if it was possible to capture. We didn't know if we would have fault motion, strong, small, rapid, slow. I mean, we had no idea. So we had no available instrument except for oceanographic type pressure gauge, Seabird 37. So we knew it was not geodetic type level, but in case we had a sudden like 10 centimeter or 20 centimeter motion, we would have been able to capture it. So we did that. It kind of helped constrain the position of the deflation source, which is modeled as like a big emptying of a deep magma chamber, 40 kilometer deep magma chamber. So this is, I can give more details, but I'm going to be very too long. So I don't want to go too deep into detail and arrive to the A0A survey. So after this first step where it was deep motion due to the depletion of the magma chamber, and thanks to your cruise, we discovered that, in fact, okay, the volcano went out, but what is threatening the population now, maybe, is an active caldera structure, a lot of venting or hydrothermal plumes in a former caldera structure. I put here on the top right. And so that's where we are a bit afraid that it could be active, and it's where all the seismicity is located. There are several seismicity groups, and there is one, what we call the proximal seismicity swarm, close to the island, on the flank of the island, and related to this caldera structure. And so we need to investigate if there is a motion, a piston motion related to this seismicity. So for that, we deployed an A0A instrument. Greg Johnson showed you a picture already. So the RBR built one very quickly because it was like the first one of the series, so we could deploy it offshore Mayotte. And these are the first data we collected. So maybe I should show you here that, in fact, when we deployed it, in fact, it was the end of the long wavelength subsidence due to the magma output. So we are now really looking for a small deformation related to this maybe piston thing. So here you have all the data with some calibration valve motion, internal calibration spot, 4 during the first deployment, 5 at the second one, and none at the last one. You can see the exponential the exponential linear drift monitoring. And in fact, after drift correction, we think we are at about a millimeter per month drift. I mean, drift difference between the two gauge. There could still be a little bit of drift. So this is for the drift correction. And then we need to remove the tides, of course. So in fact, we don't do just a tide filtering. We do in several steps. First, an harmonic analysis to remove all the known components, because if you do only like a tide filtering, you may miss like months or monthly tides. And then we also compute long period tides, because in this area they are not neglectable. It's important to take them into account. And then we do the Butterworth low pass filtering to remove all the tide residuals. And that's how we obtain what you have here. It's not corrected for drift, but it's corrected and filtered for tides. And you still have like a 10 centimeter equivalent signal. So here is the same thing, but corrected for drift. And now the question is, we are looking for small motion, and it's always the same question. Can ocean models help us lower the noise or the thing to evidence seafloor motion? So I think you already had a lot of good explanations with other talks, but here it's based on our data. So we compare our recording with 2 types of global ocean models, Gloris Renesis model and ECO2 model, so in red and blue. And then we also looked at the high frequency variability due to with the DAC correction, so dynamic atmospheric correction, the MOC2D barotropic model. And you can see that if you look at the spectra, the MOC2D model is very good as representing the high frequency variability, and the global ocean model are better, of course, for the longer period variability. And if you look at the RMS reduction, when you correct with this different type of model, you can see that so we divided in 4 band periods. So for the short periods, not surprisingly, it's MOC2D model that helps you reduce variability. And Gloris model is much nicer for a longer period, like 30 to 90 days. And exactly like Ru explained just before, global ocean models are not very good at modeling short-term variability. And here we try to compare with in-situ data to see what was captured or not captured by these models. So we are lucky because there is a glider that is surveying the area every day to look for hydrothermal plumes or new plumes and detect activity. So we were able to to compute steric height using this glider data for the first 1,000 meters and compare that with the GLORIS model. So here is a comparison. In red is a GLORIS model. In orange is a glider model. I should have said, I didn't say at the beginning that most of this work is done by Tréden Tranchant, a student with me in La Rochelle. He's postdoc now. I didn't acknowledge my co-authors, but they are on the first page. And so you can see that it's pretty different in content, frequency content, and there is a strong, you could have a strong difference, over 10 centimeter difference between the steric height measured, in situ measured, and the one coming from the model. So that can explain a big part of the variability. It doesn't give you the answer, but it can explain some part of the variability. So the conclusion of this part of our experiment is that depending on the time scale, the global ocean model here, GLORIS and ECHO, can explain part of the variability. It can reduce the RMS, but it's not sufficient. The barotropic model do a better job at reducing this variability for short periods. One point I didn't highlight when I was speaking, but it's that we use the model correction, the global ocean model correction, you need to use it before estimating your drift. It gives a way better estimate of the drift, and we were able to compare that with the actual drift measured by the A0 system. So for short-term deployment like this, when it's a few months, it's very important to account for the ocean variability before estimating the drift on your sensor. That improves the drift estimation. And here, so glider observation can be useful. And I wanted to highlight the future opportunities, in particular the future SWOT satellite, which will be an emerging opportunity in many fields and also in seafloor geodesy, because it will give us a much nicer view of the height over every site. And so we start to have the data. Another opportunity on this particular work is that we deployed now two A0 sensors, one inside the swarm of seismicity and one outside. So we are hoping to be able to see if there is some inflation deflation events related to this piston. So we will recover the data in next September. And a much longer term opportunity is France may be deploying a cable observatory on this field offshore Mayotte. So that was for the, sorry, I have many things I want to share. So I'm going to the next field, a completely different spot, a longer term work on a Lucky Strike segment, which is located south of the Azores Island on the mid-Atlantic ridge. It's a volcano at the middle of a segment. We chose this segment because there is it's one, I think it's the only one along the mid-Atlantic ridge where magma chamber has been imaged by a seismic study by Satish Singh in 2006. And it was also chosen as a compromise because it's a very good, there are lots of active hydrothermal sites that are studied by biologists. So we built a multidisciplinary monitoring observatory at this site. And I'm going to show you two continuous monitoring sites where we deploy a Seabird 53 instrument, which doesn't exist anymore, but they were pretty convenient. So it's related to the observatory, but it's not real-time data. So just to say, there is one what I call the west side is on the summit of the volcano in the lava lake, and the east side is at the bottom of the volcano. So we have several years of data. In the background, you see the raw data with the tides, and then in the foreground, it's the data where I remove the tides by harmonic analysis once again, but I didn't remove the drift yet. And then I do the difference between the two sites. I'm going to focus on that, and I'm going to focus on an event in 2015 that we see in the difference between the two instruments. And you can see that if you look only at the, maybe you can see here. If you look only here, it's impossible to evidence anything. But if you look at the difference, you have a 1.5 centimeter signal here, a slow signal. And the question is it a slow slip event on a fault, which means this one side, the east side, would be subsiding with respect to the west side, or is it a magmatic injection between the summit? So the first thing to investigate that is to look at seismicity, because we have OBSs in the area, and you can see that there is no significant earthquake at that time, like in red, for instance here. In blue here, it's not the earthquakes, it's just a derivative of this pressure gauge. So it's related to the noise in the on the seafloor pressure, but not on seismicity. So once again, the question I want to focus here is, can ocean modeling help us on that? So here are the data. Don't see anything. If you, this is the event. I mean, I'm completely unable to discriminate between here and here if it's one, which gauge moved. So we do a composite signal using GLORIS data, MOG2D data, and so this is, we add the two signal. Of course, we separate we filter data for not adding frequency at the wrong frequency. What I wanted to show you here is, in blue is our bottom pressure observation, and in green is the modeling. You can see that it's at some point it's really pretty good. So I was really hoping that it would help me discriminate between the two sites. So it's pretty good, but in fact, so here is, I highlight the area where thing is happening. But in fact, even if you zoom in, I cannot see where it actually moved. So ocean models are getting, it's better. You think we are there, but still, I'm not sure we are there, because, so here it's the same thing. So now I'm doing a running mean on the residuals. So this is the residue. In black, you have the residual, the seafloor pressure minus model. You have the residual. Here, this is the residual for the two sides. You say, okay, the residual is bigger here. Yes, but in fact, there is a drift in the whole thing. So I'm not sure. So I go back, and this is my last slide. Not knowing, I figure, since there is no significant earthquake swarm, and I think it's pretty likely that it's due to a magmatic injection. And this is also, I have another evidence that is related to the phase lag of between temperature and tides, and the phase lag change at about that time. So it's interpreted as a change in porosity over the volcano. So it's an hypothesis, I'm not sure, but here, if we do the hypothesis that it's indeed a magmatic injection rather than a slow slip on a fault, I have only 2 points, one on the summit and one at the basis. A signal that the difference in the signal is 1.5 centimeter. The absolute signal, I don't really know because it's the same on both. But what I know is the difference is less than 1.5, and the signal at one side is probably less than 3 or 4 centimeters, because I think that if it was bigger, I would see it by comparison with the model. That's an hypothesis, but it's likely that it would be out of the noise of in the model residual. So then I do a simple MOGI modeling, point source modeling, and with the constraint that it needs to be in this area 1.5 centimeter when you look at only one. Now, when you look at the difference between the two sites, so it's in this yellow part here, and it needs to be below 4 centimeters when you look at this site here. So that's how I constrain the volume, the possible volume for magma injection, and I put the depth source also. Sorry, I didn't say. Is positioned at the depth of the magma chamber that is been evidenced by seismixing. So it's a lot of hypotheses, but that's what we can do with the data right now. Thank you.